Okay. So before I go any further, I should just remind you that there is a page for Maths for IT on the Maths Learning Centre's website, and if you went to just the general Maths Learning Centre's webpage, you could click on Resources and then find Maths for IT, which is here. And we have Assumed Knowledge, Counting Techniques Revision Seminar, a Study Skills Seminar on how to do a maths exam, and one on how to write and use a cheat sheet. Interesting. Yes, okay. So just in case you're interested in looking at any of those other things. And this seminar will appear there in due course. My media was a bit dicky this morning, so I couldn't get the Maths 1A seminar from yesterday up there. So we'll just see how that goes. I'll get it up as quick as I can. Right, so we will do what I've been asked to do, which is recurrence relations / difference equations. Right. Now, the idea of a recurrence relation is that it tells you how to figure out one thing from earlier things. Okay, so your recurrence relation is that there's some sort of sequence. Does it start at 1 or 0, or does it not matter? And so on. And somewhere up here, we have an unknown term, an. That's an a. And there is some sort of relation, which means a formula, which relates an to the terms before it. And you might have to use all of them, but in the ones that you do, you have ones that use at most 2 of the previous terms. Okay, that's the idea. So a recurrence relation says that an is equal to something involving lower ends, basically. Of course, if they ask you for a definition, which they won't, you will not write that because that's fairly dodgy. But that's what it is, okay? So an is some formula involving lower ends. And some people call them a difference equation because it's usually possible to pitch it as an minus something equals something or other. Okay, and so that formula will use lower ans and also will possibly also use n itself. Just raw, like multiplied by stuff or added to stuff. And it might even use other numbers. So there's going to be some rule which tells you how to figure out an from some of the earlier terms. Now what you would prefer is a formula that just said an equals, and it was just in terms of n and didn't involve any of the an's. Okay? So you'd prefer, this is your recurrence relation. Okay? What you would prefer, what we want, is something more like this. Something involving n, somewhere in this formula. Okay? And this would be a direct equation, or a direct formula. That's what we want. So the whole idea of this recurrence relation thing is to get from this to this. Now when I was taught recurrence relations, back in the glory days when we had discrete maths too, we used recurrence relations as a way of counting things. So you had your methods of creative counting that you've learned in Maths for IT of combinations and permutations and various, and allocations and that sort of stuff. Well, there's yet another method of trying to count things, which is to create a recurrence relation for the number of things, a number of ways to arrange things, and then solve it to find the direct formula. And so you've already done some like that with the Tower of Hanoi, where you had the number of moves required is this, and it has this recurrence relation. And so you've found a formula for the number of moves, which is a way of counting things by using the recurrence relation. So that's one of the purposes of them, okay, where your an tells you the number of ways for something to happen with n things. Okay. So, lovely. It's actually quite hard, and it's very, very similar to solving differential equations in Maths 1B or in second year differential equations courses. And so the same sorts of ideas happen, and I'm not going to go through the whole theory of it. I'm going to find it in your notes and write down what it says. So let's see. I did read all of this, and I have done it before at some point in the past. All right. So there's all these different terminologies you can use about the equation you've got. The equation can be, well, the ones that we're interested in are first order, constant coefficient, homogeneous, linear. So all of those terms can be used to describe, so this is terminology. So there's a section here in your notes that talks about terminology, and it's always a good idea for any course to actually get yourself a list of all the terminology in the whole course so that you've got a nice glossary for yourself. It's not always a good plan to stick it on your cheat sheet, but it's a good plan to have it somewhere while you're studying. So the order, so while we're at it, the order is how far apart the biggest term, furthest term, and the earliest term are. They call it the index, that n, of so the latest term that occurs, so an usually, and the earliest term that occurs, maybe it's an minus 2, it's how far apart they are. So if you've got an an and an minus 2, it's order 2. But if it goes down to an minus 3, it's order 3. Okay? And in this course, you only look at first order and second order. So do be aware that if it's got an an minus 1 and an an plus 1, it's still second order because it's 2 apart from the earliest one to the latest one. So don't focus on the n, focus on find the biggest one and find the earliest one and how far apart they are. Constant coefficient means that your term, it'll be something like something an plus something an minus 1 plus and so on, okay? And these numbers in these boxes have to be constants. They're not allowed to involve n. Okay, they do not involve n. They're just constants. 3, 7, minus 1, whatever. Homogeneous means that you are able to rewrite it as something an plus blah blah blah, an minus something equals 0, or whatever it is, okay? Because it can be really awful and they can be multiplied by each other. But it's this here that's the homogeneous bit that I'm interested in. And you do learn to solve non-homogeneous ones, but only the ones that have a constant in this spot. Though there was one example right at the end where it wasn't a constant, I believe. So when I learnt it, because my course didn't have all the other stuff that's in this, it just had counting basically, we did all sorts of things with that. And then the last one is linear, which is to say that precisely that previous equation with the boxes, that you can arrange it to look like that. That you can arrange it to look like something, okay? So none of the ANs are multiplied by each other, none of them to a higher power. They're all just multiplied by something, and those somethings don't have to be constants, but they can be constants as well. But linear is in the sense that you don't square any of them and you don't multiply them by each other. So, yes. So the only ones that we do in maths for IT is that we have first and second order constant coefficient linear, homogeneous and non-homogeneous, but with that bit being a constant. Okay, they're the only ones. So we've got basically 4 flavours in maths for IT. So we have first order constant coefficient linear homogeneous, and we have first order constant coefficient linear, sorry, that's really bad writing, non-homogeneous, and we also have second order of both of those. That's what we have. At least that's what I could find. Okay? And the ones that aren't homogeneous, we only consider the case where this last thing is a 0. It's not, it's a constant other than 0. Okay. So the process of solving them is similar to the process of solving differential equations if you've done Maths 1B, and if you haven't done Maths 1B, then lucky you. Differential equations involve derivatives, and these involve differences, so this is the discrete version of a derivative, and the same methods apply quite well. I did note that there was this bit in here where he said, well, clearly this happens like this. Yeah, clearly. He had this, he said he did the ones that weren't homogeneous, and he said, well, this is the homogeneous one, and here's a particular solution. Clearly, if you add them together, it's the general solution to the whole thing. You're going, yeah, really clear. So clearly I call proof by Emperor's New Clothes. In the Emperor's Story of the Emperor's New Clothes by Hans Christian Andersen, these dudes come and say to the Emperor that they're going to build him a new cloak, and it's such special fabric that only people who are intelligent and wise can see it. And of course he goes down the street wearing these clothes made of, well, they're not really there because these guys are just pretending. And this little kid says, hey, he's not wearing anything, and everyone laughs at the Emperor. But the story goes, you see, an Emperor's New Clothes proof is, well, if you can't see it, you must be stupid. So if you say at any point in a proof, clearly, then you are pointing out to the reader that if they can't see it, they must be stupid. So do not use clearly when you write a proof. So, yes. Because it's not true. Just because you can't see it doesn't mean you're stupid, right? So you should never use clearly. Anyway, that's a whole different side story. So we're going to run through those because that's what's in your notes, and talk about how to go about it. Making the recurrence relation from the story is a different issue entirely, and I might do an example of that too if I can come up with it. Okay, so we're going to go about the whole solving of it. And the first order and the second order behave in very similar ways, and so we'll try and bring them together. So there's 2 parts to solving them, and so we're going to focus on the non-homogeneous ones. So solving. So I'm going to do the second order ones first because they're the hardest ones. Okay. So we have something like an minus okay, so that's a second order, constant coefficients, non-homogeneous. Right? The C and the D are constants. The K is a constant as well. The latest term is n, and the earliest term is n minus 2, and they're 2 apart, so it's second order. Lovely. And the first step is to find a particular solution. And there's all these rules for what C and D have to be, but in my head, if I was doing it myself, I probably couldn't remember any of that. And what I would do is I would try one, and if it didn't give me anything useful, then I would try the next one. If it didn't give me anything useful, I would try the next one after that. And that's how I would do it, because to be fair, I'm not having to do the exam, but there are rules for what the C and D have to be in order to make this work. But the way that you find this particular solution is listed here, and just give me a second. Yep. So you'll do this. Try AN is just a constant, which your lecturer calls A star. And if that doesn't work, we will try AN equals N times A star. And if that doesn't work, we'll try AN equals N squared times A star. And I'll try and show you what I mean by doesn't work. So these are later things to try if the first one doesn't work. No. If it did, you'd just try n cubed. You'd just keep going until you found one. This is only for the case where it's equal to a constant here. If it's equal to something like 3 to the n, you'll try A star times 3 to the n. So you've got to try something that looks like constant times whatever that is. And so constant times constant is still constant. And if it ever doesn't work, you just multiply it by n and see what you get. And that's true in differential equations too. You'll try something that looks like that times a constant, and if it doesn't work, you'll just keep timesing by x. But in this case, the x is n. Okay? And the way that you do that is you sub that in to the original formula, and you figure out what the missing A star has to be. Okay, so sub it in. Solve for A star. So what will happen is, when it doesn't work, what will happen is that all the A stars will cancel out and you won't be able to find A star. Okay? So in some situations, if you sub in just A star, this whole side will just cancel out and there won't be any solutions. So you won't be able to find what A star is. Okay, that's finding the particular solution. And then the part 2 is find general solution to the homogeneous case. So in this case, what we're going to do is we're going to pretend that this is equal to 0, and we're going to solve that instead. Okay, so what you're going to do is you're going to make a characteristic equation. So you're going to take this original equation, and the lowest power will be a constant, will be 1. Not power, the earliest term you'll just replace with 1. The next one will be an x, the next one will be x squared, and so on. If we were doing this for like third order, we'd do the same thing, and we'd just go up to x cubed and x to the 4, or however many of them there were. So, so make the characteristic equation, which will be x squared minus cx minus d equals 0, and solve it. So your options are going to be, it's either going to come out to x equals alpha and beta, or x is alpha and alpha. It occurs to me that it wouldn't be impossible for it to come out to complex numbers, but they don't give you that, and I don't actually know what to do in that case. You probably have to use a sine and a cos or something as your formula. So, yes, but most things in which you are counting something, where if this original formula comes from counting the number of objects that there are, you probably won't. It's impossible to get to something that would give you complex number solutions. But being a quadratic equation, it is possible. Okay? And then you have a different solution depending on which of those you have. And so in this case, So you write down your general solution, and your general solution is either AN equals that's this one here, or in this case you get AN equals K1 alpha to the N and N alpha to the N. In my head, like in your notes, it has K1 plus NK2 in brackets times alpha to the N, but in my head, it's easier for me to remember that there are two pieces in each of these. This one has 2 bits, and this one has 2 bits. And it matches with that same idea of if something doesn't work, times it by N, and you'll get something that does work. Here we have alpha to the N and beta to the N. And here, if it was alpha to the N, since there's alpha to the N twice, I'd like to use alpha to the N and alpha to the N, but I can't use the same thing twice, so since I've run out of options, I'll times it by N, and that'll give me the other one. So, yes. If I had a cubic and I got alpha, 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 I'd try alpha to the N, N alpha to the N, and N squared alpha to the N. So that it's that same idea that you just, because we need a second one that's different to that one, we times it by N, and that gives me the different one. So, yeah. Sometimes knowing a little bit about what would happen if it was even more complicated helps you to remember the simpler versions. At least that helps me anyway. Okay? And then step 3 is to add them together. Step 3 is the solution to the original equation. Now, yep, that's fine. And so we get that AN equals whatever our original one was. It's the particular solution that we figured out right there, plus the general solution to the homogeneous that we figured out here, and that's it. Okay, we are just supposed to add them, I reckon. Yes, because it's linear. Okay, and then there's often a step 4, which is that you use the fact that you know what A0 and A1 and A2 are to sub them in to figure out what the K's are. So sub in first terms like A0, A1, right, to find K1 and K2. And then you'll have this final version which has the particular and the general still, but the general won't be general anymore because you'll have actual numbers for the K1 and the K2. That's second order, okay? Okay. Right, so that's the whole process there. I won't go out any further than that. So find the particular solution, find the general solution, add them together, and then possibly sub in the first terms to figure out what the K1 and the K2 are. I'll do an example of that so that you can see where each bit fits. But one of the things about cheat sheets that's a good thing to put on is processes. Okay, having a list of things to do so that in the stress of the exam you don't forget to do any of the things that you're supposed to do. So it's not so much that, for me, I don't think it's a good idea to have examples on your cheat sheet. If you've got room, then that's fine, but you shouldn't only have an example. So it would be better to have the list of the process and an example, or an example with arrows to say the name of each bit of the process, but just having an example is not a good idea for a cheat sheet because you have to waste time reading the example to figure out what to do. But if you must have an example, annotate it to say what each bit is called so that you don't have to read the whole example, you can just read the headings when you're actually in the exam. That's my advice for examples in cheat sheets. Okay, because you don't want to increase the load on your brain. Okay, if you've and having to simultaneously read an example and figure out what you're supposed to do is too much load, and you'll become overloaded and you won't be able to do anything at all. So you need to make sure that you use your cheat sheet to decrease the overall load on your brain while you're trying to solve problems. Okay, so let's do an example, hey? I'm loath to use one that's actually in the lectures. Does anyone have a past exam with one in it? No, that's okay. I don't have access to all those things because I will use one that's in the lectures then. Okay, and we've got that D0 is 1 and D2 is minus a half. Okay, so this is just some random recurrence relation, and we just check, is it linear? Yes. Everything's just multiplied by constants and added together. Is it second order? Yes, because the latest term is n and the earliest term is n minus 2, and they're 2 apart. Nothing's multiplied by anything else, so yes, it's definitely linear. The coefficients are 1, 1, and 2, so they're constants. It's not homogeneous because of that plus 1. I'm going to have to rewrite it so that everything equals constant to make the whole thing work properly, because that's what my process says I should do. So, excuse me. Okay. That's what my process says. So this is my K here. My C is 1 and my D is 2. All right. And so step 1 is to find a particular solution. So what I'll do is I'll try normally you'd use A star, but it is a D, so I might as well use D star because that sounds like the reasonable thing to do. And so what I'll do is I'll sub that in and see what I get. So we've got D star minus D star minus 2 D star equals 1. So we've got minus 2 D star equals 1 because they cancel each other out. So D star equals minus a half. Awesome. Okay. Now that's a particular solution. Technically this particular solution does not actually match this solution because D0 isn't minus a half. Okay, but we don't need it to match the initial conditions until the very, very end. Okay, we ignore those early terms until the very end and we fix it later. Okay, so what might have happened is that I might have, if I had had D star plus D star minus 2 D star, I would have gotten 0 equals 1. I'd get no solution at all. Okay, or it could have happened that all the D stars vanished and everything was just 0 equals 0. So if that happens, then you try n times D star and see what you get. Okay, so I've found my particular solution. Find general solution to the homogeneous one. And that had the steps that I should make the characteristic equation. So I've got, now the earliest one is a constant, the latest one is the x squared. So x squared minus x minus 2 equals 0. So don't get into the trap of putting the equals 1 here, it's always equals 0. Okay, when you make the characteristic equation. So I find it helpful for me to say, well, it's the homogeneous one, that's supposed to be 0, and remind myself it's 0 first, and then write this. Okay, and then I need to solve that. Minus 2 and 1 ought to do the trick, I reckon. Minus 2 plus 1 is my, yep, okay. So I get x equals 2 and minus 1. And so the rules say that what I should do is I should do that my general solution is that dn is k1 times 2 to the n plus k2 times minus 1 to the n. If I was being clever, I would probably put the k1 and the k2 around the other way, because the 1 would go with the 1 and the 2 would go with the 2. But it doesn't matter. In fact, if I was doing this myself, I wouldn't use k's, I would just use a capital A and a capital B. But I'm going to match with what your lecturer does. So it's always good to have your own methods, but sometimes it's good to, if you can cope, use the methods your lecturer uses, because that's what the solutions in the exam will look like, and therefore, since your solution will look more like what the official solutions are, it'll be easier for the person marking it to mark it and therefore give you marks. Right? They're usually clever enough to cope, but you know, it's less stress on their brain when they're marking, and so they're more likely to find things that are correct. Right? I know that sounds really dodgy, but you know, the psychology of marking is important to know. All right, so now we have these two of them. So we've got our general solution to the original would be dn equals my particular solution plus my general solution to the homogeneous. And that's great. So I've got one step to go. So for my final solution, I was told right at the beginning that D0 was 1 and D2 was minus a half. So I'll sub them in. So when, not D2, was it D2? Probably D1. Sorry, it was D1. So I'll sub them in. So that's saying that when n is 0, D should work out to be 1. Okay, so n equals 0 into this formula that I had just here is minus, so D0 is minus a half plus K1 2 to the 0 plus K2 minus 1 to the 0 is supposed to come out to 1. So I'll put the minus a half over there. 2 to the 0 is 1, minus 1 to the 0 is 1, and I get 1.5. And for n equals 1, I've got that D1 is minus a half plus K1 times 2 to the 1 plus K2 times minus 1 to the 1 is supposed to come out to minus a half. So I put the minus a half over there, I get a 0. 2 to the 1 is 2. Oh, that's minus K2 equals 0. And now I have two equations to solve. So I'll number them. If I add them together, 1 plus 2, equation 1 plus equation 2 is K1 plus 2K1 is 3K1, K2 minus K2 is 0, 3 on 2 plus 0 is 3 on 2, and so therefore K1 is a half. And then finally I can sub that back into any one of these to try and figure out what the other ones are. So I'll sub into number 1, and I'll get a half plus K2 equals 3 on 2, so K2 must be 1, subtracting a half from both sides. And so finally, dn was minus a half plus K1, and K1 was equal to a half, plus K2, which is equal to 1. And that's my final solution, which I can just make look a little prettier if I'm interested in it. Yay! And that's the end. Okay? I recommend, if you're going to do this in an exam, to actually write those headings when you do it, because then it will be easier for you to see that you have done everything you need to do, and it will be easier for the marker to see that you have done everything you need to do. I have to say it's likely in the exam that your lecturer will do that for you. They'll say, part A, find the homogeneous solution for the whatever. Part B, find the particular solution. Okay, so they'll usually step it out for you, but if you had to do it yourself, you'll at least know what you've done. And also, it's good to have the whole process, even if you think your lecturer is going to step it out for you, because then at least if your lecturer does some of it for you, you'll be able to tick it off. So think about saying they do the particular solution bit for you, or they get you to verify that something is a solution. So they do a part of the thing for you, and you can say, yeah, I've done that bit, I only need to do these bits. Really useful to do that for yourself, so you don't waste time doing the whole thing. So, yeah. So that's second order, right? We'll go back and do the first order, hey? So what does my notes look like so far? Terminology. Yep. Just going to add back here. Okay. I will photocopy these so you can compare, like put them online so you can compare what I've done. Oh, it goes without saying that if it is equal to 0 to begin with, like back here, if that k is 0, you don't have to do the particular solution bit because it's already a homogeneous solution. Okay, so do check that. Don't need to do this bit if k is 0, and therefore you also don't need to do this bit if k is 0 because you've already done the general solution. That's the correct solution already. Okay, because the general solution to the homogeneous case is you're saying, well, what if k was 0? What would the solution be then? Okay, so do remember that. You want to make sure you don't do all the too much working. Okay, so for first order, it's supposedly simpler, and your first order equations will look a little more like just this. Okay, they're the other ones you've seen, and it's the same process, but the details are a little different for the homogeneous case. So I'm just going to see if I can make sure I match my terminology here. So first I'll find any one particular solution, and I will try an equals a star. But if that doesn't work, I'll try an equals n a star. And apparently there's a particular rule on the value of c that tells you when you should try that, but I don't remember it. I think it's 1. If c is 1, you're supposed to try this one. But it should become obvious when you sub it in, right? It'll only take a couple of seconds. So just let me come back here and find it. All right. Yep. All right, so you find your particular solution. Same as with the second order, only of course there's less options to try if the first one doesn't work. Because if that doesn't work, then this will definitely work. So this is technically if c equals 1, right? And again, you won't have to do this if k is 0. Okay? Because the particular solution when k is 0 is a star equals 0. That'll work. Like if all of the terms are 0, then obviously, if this is 0 here, if an is always 0 and so is an minus 1, it will definitely come out to 0. So you don't need to add 0, that's pointless. Okay. It's a possibility. So I'll find the general solution to the homogeneous case, so the one that has a k equals 0 at that point. Technically, you could do the characteristic equation if you wanted. It's just that it would only have degree 1, but it would work. And that might be a decent way of thinking it through. And I know that you're probably just think the characteristic equation bit in your head, but it's exactly the same and it works the same way. Yes. Just give me a second to read your notes a bit more closely. You see, you need to encourage next year's students, if you know any of them, when you meet them, say, at a welcome event in O Week or something, to come to the Maths Learning Centre more often, because the only way that we know about things is that people ask us about them. So, yeah, it's what week's too late. Otherwise, David has to figure it out during the revision seminar. Hence, for c equals 1, the general solution for the difference equation is a plus kn. Oh, it's just a constant. Oh, okay. Right. Yep, it'll work. It's all good. All right, you ready? I like this version. I wouldn't write characteristic equation on your thing, but I like it. Yep. In fact, you don't need any of that. You can go straight to here. You don't need that bit. But an is a times c to the n. Okay? It just is. Okay, that's exactly the same as it was for the second order ones, except with the second order ones there were two numbers here, right? You've got two solutions, an alpha and a beta. But with this one, your solution just comes out to a single number because your characteristic equation is only degree 1 because it's a first order. So you don't need to write that bit. You don't need to write this. But I'm just showing you how it's similar to the second order one. It's exactly the same. Even if c is 1, it'll just be a times 1 to the n, which is just a. Okay? So it'll always work out that way. And 3. Find solution to the original. And so you'll get an is the particular plus the homogeneous. And then the step 4 is, what did I call it when I did the working out? The final solution. Which meant that you had to sub in the early terms to find a. So I'm the sort of person that if I did this myself, and when I was lecturing it, I wouldn't use K1 and K2 in the second one. I'd use capital A and capital B so that it looked more like this one. So in order to understand things and remember them, you want to make them as connected as possible. These two processes for first order and second order are the same. It's just the second order one has a slightly more complicated bit just here, but it's still the same because the second order one has something times something to the n plus another thing times something to the n. And there's two of them because it's second order. So you can imagine what would happen with third order and fourth order and fifth order. It would all work exactly the same. It's just that that bit there would have more things to the n in them. Okay, so your example is something like an minus a n minus 1 equals 2, a0 equals 2. And we'll solve that. So first, find a particular solution. And so we'll try an equals a star, and we'll get a star minus a star equals 2, 0 equals 2. That's a contradiction, so that's not going to work. So we'll try an equals n a star, and so we'll get n a star minus n minus 1 a star. So notice that this was an minus 1, so instead of n here, I need to use n minus 1 when I sub it in. Equals 2. And so we get n a star minus n a star plus a star, so we get a star equals 2. Okay? 2. Find general solution to the homogeneous case. And so we'll think about our characteristic equation. It will be x minus 1 equals 0. So we'll get x equals 1. And so my an will be a times 1 to the n, which is just a. See, I didn't write that bit down. I would have, I'd probably write, x minus 1 equals 0, x equals 1. Okay, cool. That's my bit on the side of the piece of paper that I wrote to try and figure out what was going on. And that's just a, because 1 to the n is just a. 3, find general solution to the original. So we've got that an is my original solution 2. Sorry, it's 2n, isn't it? Because it's n times a star. Sorry about that. Yeah, the a star equals 2. So an is in fact 2n. Sorry about that. Didn't do that bit back there. See, I figured out the a star, but I had to sub it back in to figure out what an is. I had to sub that back in there. So it's 2n plus a. And then step 4, final solution. I've got that a0 would be 2 times 0 plus a, and a0 was supposed to be equal to 2. And so therefore a equals 2, and so an is 2n plus 2. So overall, the first order ones are shorter, right, because they're first order. But it's the same process for both. And that pretty much leaves coming up with one of them, right? Coming up with a recurrence relation in the first place. And that's not always the easiest thing to follow through. What I would really love is an example that's not in the lecture notes of that. Have past exams had any where you had to make one up yourself?
Not that I've noticed.
All right then.
You're welcome to look at the exam.
Sure, let me have a look at it.
Could you just push it up a bit? I can see what's going on. Thank you.
Is it just me, or is that this semester?
Yeah, that's from this spring. I know when I printed it off, I was getting really excited. I was like, yes.
Well, what year is it? What year is it then?
Supposed to be 2012, so it's semester.
But the 20, does that mean that both of these are 2012?
One's discrete and one's
Oh, right. So do they give you the one where you write in the gaps? Yes. Or on the other page, because there's never enough room in the gaps. Okay. So the recurrence relation that they've got in this one is not one that you use in this because it's not homogeneous linear. So that's just an ordinary induction thing. So sorry? Oh yeah. That doesn't make any sense, right? Because you have recurrence relations in discrete as well under induction. Huh. No, they just give you one. All right. I don't think they're going to give you. I really don't think he's going to give you one that. Yeah. So the one in the previous year is just one where they've given it to you as well. You'll notice that it seems likely that they'll give you a second order one, because both of them are second order. And it's only a sample of 2, so we can't be sure, but it seems likely. So I'm happy to not go through the making one up of your own, but usually it's to do with splitting it into cases and thinking about what happens with the first one or the second one. So the example that's in your notes, it's also with the n-bit strings. An n-bit string is a list of n binary digits, blah, blah, blah. So you want to count how many of them don't contain 111. Okay, so you know how many n-bit strings there are. It's 2 to the n. Okay, because there's 2 options for each digit. They can be 0 or 1, so that's 2 options for each. So it's 2 times 2 times 2 times 2 for however many there are. And that's from your probability counting thing. However, and we could count how many of them. We could probably count in a different way how many didn't include that pattern 111, because we could actually find the position where the 111 was and put all the rest of the digits in. Okay, so you could go, well, if the 111 was right at the beginning, then we've got an n-3 bit string for the other end. If the 111 was in this bit here, we've got many of them, but we've also double counted the ones that have 1111, and so we could have counted it that way, but it'd be really hard to count it that way. We'd have to use inclusion, exclusion, so it's much easier to count it this way, where we go, all right, well, why don't we say, if we knew how many n-bit strings there were that didn't contain 111 of a certain length, then we could figure out how many were for a bigger length. So we could go, well, if we chopped off the first digit, the rest of it doesn't contain that. So we have, if they begin with 0, then we've got an n-1 digit string that doesn't contain 111, so that's good. If they begin with 1, well, we don't know, we need to consider the next digit too, because the first digit could be 111, could be 11 there, which would be a problem. But if it starts with 10, that's okay, we can just have n-2 of them, like a length n-2 in this spot. And if, in part C there, if it starts with 11, well, the next digit would have to be a 1. We've got the options, either this is a 1, in which case we've got one that starts with 111. So we know that that next digit can't be a 1 if it doesn't contain 111. And so we have now n-3 over here that don't contain the rest. And so you can make your string like that. And I'm really hoping that when I go to the next page, that's precisely what happened. That's right. Okay, so they're often using what happens if you know in some spot, you can figure out another spot. All right, I'm just going to actually stop the video and upload it, and then record the just general requests bit, if you have any requests, after. All right, so the question for the video was, how do the particular solution and the general solution relate to each other and to the equation itself? That's the sort of idea. All right. I think someone at some point in the past came up with this cool idea that particular and general solutions are a good way to go for many different situations. That's the history of it. I don't know who did it first, whether they did it for recurrence relations first, or whether they did it for differential equations first, or whether they did it for matrix vector equations first, because they come up in all of those situations. And it's all to do with situations where you have an equation that comes out to zero. So the idea is that an equation that comes out to zero is easier to solve than an equation that doesn't come out to zero. Okay? So if you have any sort of thing, pardon me, that you put things into and it comes out to zero, right, and you've got stuff, then in general, if all those things are zero, that will be one of the solutions. Okay? So that's the general thinking behind all of these situations. So if you have some sort of formula where all these things you put in and it comes out to zero, in general, thing equals zero is a solution. All right? That's the big idea. But also, what if you then had something, yeah, I'll do it with recurrence relations, okay? So the idea is that you have a sequence, right? And you're told that no matter what the numbers are that you're up to, you're told that C1A, C0AN plus C1AN minus 1 plus C2AN minus 2 plus, and so on, comes out to 0. You're told that, right? And so you know that if that one solution would be, okay, so you get a solution is that A0 is 0, A1 is 0, A2 is 0, and they're all 0, okay? So AN, i.e. AN is 0 for any n, okay? So that's one idea, right? So if the entire sequence is 0, 0, 0, 0, 0, then it will work in that equation, okay? That's great. If there are any other solutions, they'll also work in that equation, and that'll be good. And here's the big idea. The big idea is that what if we had some other solution? There might be some other solutions, okay? There might be more, right? And there might be whatever they look like, okay? So AN equals whatever it looks like, okay? With an n in it, some formula that has an n. Okay, so that means that when I sub this into the formula, right, I go C0 with an n in that spot, plus C1 with an n minus 1 in that spot, plus, and so on. It will come out to 0, right? That's the idea behind it. Okay. Excellent. So there might be more, there might be infinitely many of them. Okay? Right. What if, instead of it coming out to 0, we wanted it to come out to k? Right? But now, we want it to be equal to k, right? Right. So we've got C0 AN plus C1 AN minus 1 plus equal k this time, right? Now we know that none of those solutions back there are going to work because they come out to 0, right? This solution here comes out to 0. This solution, where they're all 0, that comes out to 0. So none of them are going to work for k. Okay? Good, we're doing well. If we happen to find one that works for this, right? So suppose we found a solution. Do it as a circle this time. Okay. Then that would mean that C0 equals K, right? Okay. Here's the magic of linear things. This is all to do with linear things. So this is a linear equation. Okay. The magic of linear equations is that if I now add any one of those ones that came out to 0 to this, watch what happens. Okay? I know this isn't very good maths, doing it with squares and circles, but it makes sense to me. Okay? I don't want to confuse myself by putting in F's and G's or anything like that. I want to understand it, and then if I wanted to do a proper proof, I could put proper notation in. So C0 times, right? That's AN plus C1 times and so on, comes out to K. But I can, because it's linear, I can expand the brackets. Yep. I don't know if this is going to come out to K yet, right? I want to see whether it comes out to K. I'd like it to come out to K. But look, this is my bit with the squares, with the rectangles. So I've got C0 square bit that's those bits. And I also have C0 round bit yep. And the magic is this bit comes out to 0. I knew that because look, that comes out to 0. And this bit comes out to K because I just said that back here. This new solution that I just made gives me K when I put it into the formula. So, no matter which solution I had to the one that comes out to K, and no matter which solution I had to the one that comes out to 0, if I add them together, when I put it into the equation, it'll come out to K. So if I get any one particular solution to the one that comes out to K, and I add on all the possible solutions that come out to 0, what I should get is all the possible solutions that come out to K. That's the idea behind why you're allowed to add the particular to the general. Okay? That's part 1, right? So that's why you can add. So AN equals that plus that is a solution for the equals K version. Okay. No matter what I pick for either of these, it will still be as long as this one comes out to K and this one comes out to 0, it'll still come out to K, even if I add them together. So what I do is I take all the possible answers that come out to 0 and add it to any one of the answers that come out to k, and it should give me all the other possible answers that come out to k as well. Right, that's why that works. The other part of the story, so that's the particular general idea. And that general concept happens with matrices, it happens with differential equations. Anything that you have linear thing comes out to 0 or linear thing comes out to something else will work that way. And you don't have to have these c's being constants. As long as it's possible to factorize them and expand brackets like this, then this will work. Okay? And that's what linear means. It's possible to expand brackets like this and factorize like that. So as long as it's possible to expand brackets in a reasonable way, then this idea of particular and general will work. Okay. The next bit is, why are you getting all these powers of n everywhere? Like when you actually, guessing your particular solutions, it seems reasonable that there will be one that's just constant that will satisfy the result. Okay, because it should be possible to, you know that with the equals 0 case, all of them being 0 will give you the right answer. So it seems reasonable if it comes out to k, all of them being the same number should give you one of the solutions if you pick the right number. So that's why the particular solution for that works, for the equals a constant. Why the times n works is all a bit puzzling, and sometimes it's just the wisdom of our forefathers who have given it a go, and they go, yeah, it works. Okay. But it's also to do with the fact that when you subtract n and n minus 1, you get a constant. And so the concept is that, at least with the first order ones, if an is something times n, if you're in that situation, and this is, a star times n, and this is a star times n minus 1, then what you'll get is just a star n minus a star n plus a star, and you'll just get a star. So the concept is to do with, in some special situations, what you actually have is a pure difference equation, which just tells you the difference between one term and the next term. And so the classic version of a difference equation is 1, 2, 3, a difference, one that satisfies that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That sequence, everything's 1 apart. And 2, 4, 6, 8, 10, everything's 2 apart. 3, 6, 9, 12, everything's 3 apart. So those things are 3 times whatever number you're up to, 2 times whatever number you're up to, 1 times whatever number you're up to. And so if everything's the same distance apart from one to the next, it should be just a multiple of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that's why you try the n times constant as a solution, because you expect that it ought to work, because you know that that works for some other situations. And the powers is a similar idea, that it's to do with knowing that sequences that have powers in them behave in certain ways with their difference equations as well. So I'm making most of this up on the spot, just be aware, I'm not getting this from anywhere, it's just thinking about it. So a pure difference where there's no terms other than just a minus should be n times constant. Like it should be, 1, 2, 3, or 2, 4, 6, or 3, 6, 9, that sort of thing. That's the idea. Okay. So I guess the idea with the homogeneous one is that you want it to come out to 0. So in the case where it's a pure difference and it comes out to 0, then if you choose them all to be the same number, it'll work. You know, an and an minus 1 are the two terms next to each other, and you do the difference and it comes out to 0, they'll be the same number. So choosing the whole sequence to be 4, 4, 4, 4, 4 should do the trick. Okay, so in that situation, and the other situation is that, let's see, something like that. We use recursion or even induction to prove that it ought to be a power times something. Because we think about the first one, A0 is some constant, maybe A. A1 will be C times A0, so it'll be CA. And A2 will be C times A1, which is C times CA, which is C squared A. And A3 will be C cubed A, and so on. And so you'll end up with AN equals C to the N times A. And so you expect it to be powers, and because it works as powers for just a first order, you expect that it might work as powers for the second order as well. And that's just what you expect might happen. And so it turns out from the wisdom of our forefathers that if you solve that characteristic equation and chuck them in powers, it'll just work. Because powers ought to work in situations like this. So, yeah, that's my understanding of it. Yeah. Okay. Any other questions about anything else anywhere in the course? While I'm still here, I've got another 25 minutes before your lecturers turn up in the Maths Learning Centre for you to ask them personally.
Do we have to treat it any differently if we're given like a two, like say AN and then AN plus 1 and AN minus 1?
Oh yeah, so for the recording, the question was, what if something like that? Yeah. No, you don't have to treat it any differently. I would just convert it. I would go, all right, well, I'll just sub in n minus 1 into everything, and everything will go down a power. So that's the same as an equals an minus 1 minus 2 an minus 2. And then I'll start from there. That's what I would do. It's the simplest way. But you don't technically have to treat it any differently. You just go, well, the difference between the lowest and the highest is 2, so it's a second order. The lowest power will be your constant term in your characteristic equation. The second last will be your x, and the highest will be your x squared. So you could do it direct from there, or you could just put everything down 1, or as many as you need to get to wherever you want to go. So you're right, in your Fibonacci sequence, it's normally written as like that, and you can just go, all right, well, that's the same as this. Just subtract 2 from everything and I get a nicer equation. It's just that you start in a different spot, right? So this one might start for, this might be n is greater than or equal to 1, but this one will be n is greater than or equal to 2. Yeah, because that n there would be a 1, but this n here has to be a 1, so n has to start at 2. All right.